So good morning, everyone. Welcome to this webinar, intermediate level workshop, Earth Observation with Julia. My name is Nathanael. I'm head of data science, cloud infrastructure and development at the Atlantic International Research Center. And we have with us also a representative from the United Nations Trade and Development. We have more people from the Earth Center, and we have guests, panelists from Europe and from the United States. Great contributors to the Julia programming language, especially to the Earth observation ecosystem. So welcome all participants. We have over 40 participants registered, mainly from Brazil and South Africa. I will introduce the Earth Center just briefly. I think most of you already know the Earth Center well. And then I'm not sure if our colleague from UNCTAD also wants to say a few words. So the Earth Center works in many areas. The Earth Center is a non-for-profit organization, and it works in areas such as clean and productive bays and estuaries, the resilience to coastal natural hazards, sustainable food production, improved management of marine and coastal resources, improved environmental and maritime monitoring. So we work a lot with Earth observation, but our main focus is to create services. Use Earth observation and other data, create services that serve the scientific community, that promote job creation in a knowledge-driven economy, and always with careful attention to the UN Sustainable Development Goals, in particular to monitor and contribute to reach these goals. One practical example of one of the services we started providing here in the Azores is the risk of sporulation of a particular fungus that impacts the cows, their health and the milk production, etc. So created a web application where every hour we let the users know of the risk for the cattle, protecting the cattle. Another one is something more recent. We're creating a service that is global monitoring of internal waves in near real time. This is a machine learning-based web service with supervised learning and an image classification platform. We have an infrastructure, we have a data center, and we follow several satellites. We get data in real time that we process. We also have access to high definition imagery, and we were involved in the creation of the Azores IoT network based on technology LoRaWAN that we are expanding throughout the Atlantic. We also involved in the creation of a constellation in Portugal and Spain with around 16 satellites that are specifically focused on the Atlantic. We are part of several international networks. We are part of the United Nations Environment Program. We are one grid node, and we provide data for the program. We are part of the MBON Marine Biodiversity Observation Network. We are the General Secretariat for that. We are also an ESA laboratory, a European Special Agency, and we're part of the RCTS and Joint Networks. These are scientific networks for computing. We are located in the Azores, here in the middle of the Atlantic, as you can see right here. But we're heavily connected with partners, associates a bit throughout around the Atlantic. So what brings us here today is this project that we've been working on with United Nations Conference for Trade and Development, UNCTAD, and in particular, this project called Harnessing Space Technological Applications to Sustainable Urban Development. This project is delivering value. It has two recipient countries, Brazil and South Africa. And in Brazil, we have this contact with LIMES. It's the organization in Brazil, in Rio de Janeiro, that is helping us set foot on the ground and organize one event. And SANSA, the South African National Space Agency, where that is our safe partner on the ground in South Africa. We had our kickoff in the beginning in January of 2024. Then we had where we have people from South Africa and from Brazil, participants from these two recipient countries. Then we had an in-person event in Brazil, in Rio de Janeiro, a workshop with 42 attendees in person at LAMS between the 3rd and 5th of April 2024. Then in August, we had an event in South Africa, in Pretoria, with 49 attendees, organized with SANSA, 6th to the 8th of August. And today we have the 4th event of this project, which is the remote-only workshop on the 20th today of November 24. Finally, then in January 25, we are going to close the project during the event JuliaGeo 2025, excuse me, which will take place here in the Azores between the 6th and 10th of January 25. So most of the project is behind us now, and today we have while the workshops in Brazil were in South Africa were more introductory workshops to Julia for people who work experts who work with Earth observation. Today we have the topic of the workshop, or the content of the workshop is a little more advanced. So this is the context, the reason why we're all gathered here today. And we have, I'm not sure if our colleague, so Eugenia is here, Eugenia Nunes from Untitled. I realize now that is online. So Eugenia, I will pass the word to you if you'd like. We also have with us Fabio Okhana, who is our colleague from LAMS in Rio. I don't see here now on my window when it's just me. I can see representative from South Africa, but I'm sure they are present. Eugenia, would you like to say some words?
Sure, Joel. Thank you very much for giving me the floor. I just wanted to welcome everybody here today. My name is Eugenia Nunes. As Joao just mentioned, this activity is part of a project with the United Nations Trade and Development and Air Center. And I just wanted to welcome everybody here, and especially a warm welcome to our partners in the field that have benefited from this project. Fabio, who is from Brazil, and Nale, I don't know if she's online, I believe so, from South Africa. And I just wanted to wish you all the best, and hopefully we can have a very good workshop. Thank you.
Thank you very much, Eugenia. So our agenda today starts now in a few minutes with the power of JuliaGeo by Mr. Alexander Barth. Then we might have a small break if necessary. Then Julia use case for change detection, Mr. Felix Cremer. Then we might have another break. These are 1-hour sessions approximately, so we might need those breaks. Then another session will be the GeoRegions ecosystem, use cases for NASAPrecipitation.jl and Area 5 reanalysis.jl by Mr. Nathanael Wong. Mr. Nathanael Wong is in the US and he didn't join us right now because it's very early there, but he will be joining us throughout the first 2 sessions. And then eventually another comfort break, and then project work in Julia using DrWatson.jl and Pluto.jl also by Mr. Nathanael Wong. Then at 16:50, this is all CE time. The closing remarks, some Q&A if still necessary, and then next steps and farewell. Next steps, we're going to just let everybody know about the next event. It's Julio 25. Q&A, I suggest that for those who are, everybody who's attending, you could write questions in the chat during the process now, during the presentations. And the presenters will do their best to try to, at the end of the presentation, check the chat and reply to your questions. So after the 15-minute session, there will be a short moment to answer those questions. Feel free to just keep dropping the questions as we go along. I think that's it for now. Thank you very much for being here, for participating. We believe this content is very interesting and very useful if you're working on Earth observation, especially if you're working with Julia. We are a little early, but since we have attendees online already, and we have Alexander Barth, which is the first speaker here. Alexander, would you like to start?
Yes, of course. So thanks a lot. Let me share my screen. Share. Okay. Let me go to the first slide. Yeah. So thanks a lot to the Air Center in UNCTAD for organizing this great workshop. It's always a really nice opportunity to speak to other members of the Julia community or community and to users. So it's really nice to that we have organization like the Air Center, which is so active in the Julia community and organizing all these events like the Julia Earth observation meetings, which are always great opportunities, great events. So I will speak about, give an overview of the JuliaGeo ecosystem. So I will briefly talk about different packages in this ecosystem. Also mentioned a bit more detailed my package that I work on. So a lot of code development in the Julia ecosystem is done via GitHub, and so everybody can contribute code to GitHub, and this either will be done using a personal repository or organization. And this helps a lot to work together with other people and to iterate on code. And JuliaGeo is such one of this GitHub organization, specifically for the Julia language and the geospatial problems. So we have this is a link of the JuliaGeo organization, and also this is a general web page for JuliaGeo organization. So there's a quite active community. So we have so far currently 27 members and 4 outside collaborators. So all 27 members has essentially access to all of the all repositories, all codes, packages in JuliaGeo, and the outside collaborators only to some specific packages. So you will recognize names like Felix, which will talk after me, for example. And yeah, so I give you a very brief overview of the different packages here and some related packages which are outside JuliaGeo. Not all packages are inside JuliaGeo, so some of my packages are not part of JuliaGeo, but I mention them also here because I think that might be interesting to you. So I will group this a bit into different topics. So either when you work on raster data or on vector data. So for the raster data, there's a very influential format which is called NetCDF. And one of the oldest packages inside the JuliaGeo ecosystem is called NetCDF.jl by Fabian Ganz. And this allows you to read NetCDF files in the Julia ecosystem. So NetCDF are typically raster data, but I will give you more information later on in this. And there's also another package which is called NC datasets. This is one of my package, I would say. So it is provides a high-level interface to operate with NetCDF files. And there are also similar packages like GRIP dataset and ZAR dataset, which provide essentially the same API working with other file formats like GRIP or ZAR data to access the data essentially with the same API. So the constructor function is different, but it's essentially the same operation are also available to you. And this data set are quite these formats are really well used, quietly used to provide use Earth observation data, satellite Earth observation data, but also model data, ocean data, atmospheric data. Okay. And there is another package which is called tile provider that allows you to access tile data sets or image data sets from different tiles, maps data essentially. And for vector data, there are different formats that are commonly used. So one is the shapefile format, and there's a package called shapefile.jl, which allows you to read shapefiles in Julia. And there's also GeoRegions, so a profile, specifically profile of the JSON format, specifically tailored for JSON for geodata. Okay, and GeoParquet is a binary format for JSON for vector data that's sometimes more efficient if you have a large number of data. And there are some other data sets which allows you to directly access like the boundaries of administrative areas, like GADM package, or geodata set is one of my packages that allows you to load, for example, land sea mass or the coastline of the Earth. So essentially, this is made, for example, for plotting purposes, for visualization purposes, and the natural Earth is also an interface for natural Earth data. So there's a lot of data which have several repositories which have a package associated to it, so that you can easily import them in the Julia language. And there are some packages which work more on the description of data, like GeoInterface packages, which allows you to work with points, line segments, and so on, polygons defined on the Earth, and map tiles that works with tiled web servers. And there is so I mentioned before the NetCDF, GRIP, and ZAR datasets. So there are a lot of common code for this packages, which is available in a common data model package. Another very quite important package, it's called rasters.jl. It should have been in the list. Sorry for not mentioning it, but it allows you to work with raster data, and it is actually one of the data. It's one of the foundational packages is dimensional data. And later on, Nat will speak about the GeoRegion package, I guess. It's a package for querying and extraction of region-based data. Not all of the development is done inside the JuliaGeo organization. Not all of development relative to geographical or geoscientific data sets. There's also the Julia Climate organization, which 37 members, and several members of JuliaGeo are also members of Julia Climate. And Nat will also speak about another organization that he founded. It's GeoRegion ecosystem. And for visualization, maybe it's good to mention also the Maki.org, the Maki.org organization, and the Julia Plots for visualization. Okay, so when you start data exploration in Julia, it's often start with loading and importing the data. And that's probably the first hurdle that you have to overcome, and how to get your data efficiently in the Julia session. And here we'll speak more about one particular format, which is called NetCDF, but it has been quite influential for other formats as well. So a lot of things that I say here now apply similarly to other raster data like ZAR data, ZAR or GRIP data. Okay. So NetCDF has been maybe quite influential because it's very flexible format for storing all sort of metadata. And it's a binary format, which means that you can load the data efficiently and also cross-platform data. So even if previously, when maybe 30 years ago, when a lot of people were using Fortran, when you save your model output on one machine, it does not you cannot easily load this data set on a different machine because the data is actually quite strongly platform dependent. And NetCDF is actually solve this problem for us because it's an efficient format and it's cross-platform. But NetCDF is just a container, so how the data is stored on disk, and on top of this you have the CF convention, which gives the semantic meaning of the data. So for example, if you want to say save temperature, you have to annotate that this data is actually means temperature. And it's not just an array which represents maybe precipitation or something else. Okay. And one very central aspect of NetCDF is the concept of named dimension and shared dimension. Okay. So if you have a three-dimensional temperature, maybe function of longitude, latitude, and time, yeah, or x, y, and t. And so you give the dimension different names, okay? And likewise for coordinate variables like latitude, temperature, latitude, longitude, time, you would equally annotate these dimensions. So, and by the mere fact of giving the dimension a name, you can use NetCDF for all sorts of different cases. For instance, if your grid, your longitude latitude grid is no longer constant time, but varies in time. So this is something that you can easily represent with this kind of data set, with this kind of format. So even time series or transects or static or moving grid, all this is naturally can be expressed in NetCDF with shared dimension. And yeah, so this is quite useful and has been also adopted in the context of different formats like CISAR format. And there is no hard distinction between coordinates, longitude, latitude, and the data. Okay, and this is also a very interesting choice to make because what is metadata and what is data is actually sometimes quite domain dependent. Okay, so as an oceanographer, temperature is always a data variable, but for somebody who looks at oxygen in the ocean, temperature is quite important for this application as well, but it's rather considered a metadata, a data that helps to interpret the oxygen content, for example. So therefore, it's quite nice that in NetCDF there's no distinction between coordinates and data, and only the shared dimension are told how the different arrays vary. And there are different formats. So there's the original NetCDF 3 format, but the newer NetCDF library can also support HDF5. And also opened up with remote dataset. So if you have the data living on the OpenDub server, you can actually use this data without actually explicitly needing to download the data. So the data is really downloaded directly to the memory of your computer. And ZAR files are also integrated in the NetCDF library. And for example, for Xarray, the Python Xarray package, they added the concept of shared dimension to ZAR as an extension because it's so useful for geospatial data. What is also quite interesting to see is within the wider ecosystem, where is NetCDF actually used? So you can have a look at the dependency graph of what you see here in the center. That's the NetCDF see packages, and then you see how the different packages depend on it, like NC dataset here or NetCDF.jl, or all the packages out of it. So there are actually quite a few packages in the NetCDF ecosystem who depends directly or indirectly on NetCDF. And this only counts for the packages which actually process NetCDF data. We don't see any dependencies which do not have a strict dependency on NetCDF, but only do some computation with it. Okay. So as I said, NC dataset allows you to read and write NetCDF files, and what you see here is just an example. And all of this should also apply to ZAR, GRIP, or TIFF datasets. So the idea is that you just take the general concepts in Julia, like arrays, dictionaries, and then map the general concept of NetCDF or attributes, dimension groups to these variables. So for us, NetCDF variables are just behave the same way as Julia arrays, and attributes behave just the same way as dictionaries. So, and this leads to a quite natural API, I would say. So in order to open a NetCDF file, you just calling the constructor NCDataset without an S this time. So the module is NCDatasets with an S, and the constructor NCDataset without an S. And once you open this dataset, you can just typing just the S in the shell will print in the Julia REPL will print all the contents, all the metadata, and to access a particular variable, you just index this dataset. And to load a particular variable or a slice of the dataset, you just index it as it were an array. Okay. And within the CF convention, you have a lot of additional rules that are applied, like fill values, like missing elements are annotated with fill values, and there's also scale factor and add offset to apply a linear transformation. And time variables are generally encoded as dates since a starting date, dates since the 1st January 1970, for example, and they are recognized and automatically converted into Julia date time objects. So you can manipulate the date time as you would with any other dates. You can compute differences of dates and extract months, years, for example, out of it. But within the CF convention, there are also other time definition defined, and like they have also been implemented, but in a separate package. One of my separate packages was called CF time, where you can have other calendars like standard date time or Gregorian proleptic Gregorian calendar and Julian calendar. So so this is also available in CF time. And you can also always access the raw data. And something that we are that we are looking quite carefully is also the performance. So I recently looked at the performance of the CF time packages, and it was actually quite comparable, for example, to NumPy, and even faster in some cases. So a NetCDF array can be easily subsetted just by providing the indices, as you would subset a regular array. And you can also chain all these operations. You can first access a temperature in the dataset and then subset it even more. And if you want to subset not by indices, but by values, say I want to have the longitude or the latitude within a given range. So we help this with a given with a select macro. So we're saying we want to select all the data where the longitude is between 10 and 20 and the latitude between 30 and 40. And this also works with other dimensions. So NetCDF files are quite often used for georeference data, but not only. So if you have another dimensions like frequency, if you work with hyperspectral data, So you can also make a selection based on this kind of dimensions quite easily. And just if you have any questions, I don't know if you don't hesitate to ask anytime. So, so there is also what we recently implemented is, or recently maybe 1 year ago, we implemented the ability to group and reduce data set, which is something that's quite commonly used in the context of Python's X-array package. So, for example, if you have your SST, and the SST, that's the netcdf variable as it's stored in the netcdf file, or SAR or TIFF file. You can easily group this data by months and compute, for example, average. And we really try to make this syntax quite natural, by using group by and mean. And so, and here time is actually one of the dimension which, as it is defined in the netcdf file. Okay. An SST mean is actually not the result already, just a lazy array. So only when you index the array, you can get actually the result. So you can, this operation is really inexpensive to do because it doesn't do yet the computation. But when you say, okay, I want to group by my months and compute the mean, but in the end, I probably need the first month, just January, you would just index the first month and it will only compute the first month. Okay. And as what you can do in Julia, which is quite powerful, is the broadcasting operation. So when you come from MATLAB or another language or Python, you see that in Julia you would need to write quite often a function named dot or operator dot. Okay, so even though that might be a bit annoying in the beginning, it's a really very powerful construct because it allows you to write a function which just works on a scalar, and then you can work efficiently on arrays as well. And here we use this broadcasting operation. When you group the data, you can apply before computing the mean any kind of function. Okay, and this will be done basically. For example, you group the data by months, and then you apply a function, maybe looking at if the temperature exceeds the threshold. This is something simply applying by the function dot, because what the group by returns is essentially a lazy vector of arrays. Okay. And another thing that we implemented is that, so once you computed the seasonal mean of sea surface temperature, for example, what we quite often also want to know is the anomalies. So now I computed the mean January temperature, but I want to know if the January year 2024 was actually quite different than from the mean. And therefore, so this is computing the anomalies, how this month is different from the mean condition. And this is also implemented by broadcasting operation. You're just essentially taking the difference between the sea surface temperature and its monthly mean. Okay, and behind the scene, we will subscribe every data set with the corresponding months. Okay, and it is very flexible, so you can also use different operation, like you can use so it does not only work with the standard operation like mean and standard deviation. You can use any kind of operation. You can easily integrate any kind of operation, and you can, for example, base your time selection not only based on months, but maybe is it within the Atlantic hurricane season, which is defined between months 6 and months 11, end of month 11. So you can use this kind of you can use actually any kind of aggregation. Okay. And so now an important question is, so is it is actually fast. So it is not really sufficient to have a quite flexible library. If it's much slower than something else, then it's not really compelling thing to use. So here we compare it with Xarray, which is in Python really maybe the de facto package for doing something like this. And we're using a three-dimensional array of 360 by 180 grid cells. So it's more or less represents the data set, global data set at a 1 degree resolution. And we have 30 years of daily data. So we have 30 times 365 normal times. Okay. But we're using just random data in order for this test to make it more easily reproducible. And we're actually computing the mean and the standard deviation of the data group by month. Since it's random data, we already know that the mean is 100 and the variance is 1 because we choose these parameters when we create the random data. And we store the data in floats in single bit precision. And we are actually also computing the accuracy using double precision. Okay. And yeah, in order to make it something which is quite important to consider when you do benchmarking with code that reads data from the disk, is that the operating system behind your scene actually caches the data. And this is something that you want to avoid, but because it doesn't really, it's not really representative of your actual work that you would do if you work with a new data set. So we're dropping the file cache before every computation in order to make it in order to make it more representative. And also we're using just one CPU core. And so this is, for example, the results when comparing Xarray and our common data model. And we see that we are actually quite good. And so maybe around 1 second or 2 seconds faster. So maybe around 20% or 10 to 20% faster than Xarray on this machine, and with a very similar accuracy. And if I'm using a different machine, actually a machine with a faster hard disk, then actually the difference are even larger here. So we are almost 50% faster than Xarray in this case. And this was a bit of a surprise for us because Xarray, well, it's written in Python, but all the computation themselves are done in C, so it could be actually quite fast. Okay. And so by looking actually why what was actually the difference between Xarray and our model, our tool, we actually found that Xarray, when you're computing, let's say the mean, the monthly mean, it loads first all the data sets, all the data for January, computes the mean, and then all the data set for February, compute the mean, and so on. Okay. So while the data is stored on the disk, when you read the data, it has to jump from different parts on the data sets. Okay. And so these are essentially seek operations which can be slow. Okay. So even on a solid state disk, as these tests are made, this is something relatively slow. But what we did in common data set, we actually loaded all the data sequentially. So we load all the data and then decide for every slice, okay, you are a January slice or you going to the February slice and so on. Okay. And so this is something that you can easily do for some operation, like sum, mean, variance, standard deviation, minimum and maximum. So the data is loaded sequentially, which gives us our performance benefit. For some operation, this is not possible, like the median. So therefore, we're using essentially the same approach as Xarray. But I think the sum and the mean and variance is such common operation that they're quite worth to be treated, especially if it's faster. Okay. So all of these codes actually also available on this address here, on this common data model package, the documentation of common data model, and so you can access to this link here if you want to follow along. And since this is a workshop more focused on sustainable development or on sustainable urban development or urban data, I was looking what kind of example I can choose. And here I use actually an example of the of flooding. Maybe you're aware of the terrible flooding that happened in Spain in the Valencia region around the 2nd November, and even it's going on. And so I create an example now, not with NetCDF, but with GeoTIFF, and you see that you can do exactly the similar operation on this. And so if you want to follow along, so this is the address, it's a tiny URL address, geotiff-julia, and you will see here we are actually accessing the data set from the Spanish coast, where you see this area which was flooded by this terrible event. Okay. So here we're using the data from the NASA World View. This is a very comprehensive archive of data. And so essentially, when you're on this web page, you can add. You have a lot of different data sets. Slow to load for me. Okay. But it's not a problem. I just wanted to show you how to extract the data there. But essentially, you have to click on Add Layers, and then you can actually choose the name Flood. So you have a lot of layers, so it's easier to just search for flood and then add the layer to the data set. Okay, here, if you are here, you can just add a layer. And here, look for floods. And we are working on this kind of data, on the flood 3D averaging window, conversion window. And this is a global data set based on MODIS data. And on this server, you can only have the data for the last 7 days. So the 2nd November is no longer available here, but the links are still live here. So I saved the links, and so you can still download the data themselves. Okay. So essentially, the data are organized in granules, or you can think of it as tiles. And so these are rasters, longitude and latitude, and time. And so for every pixel, you will have 3 different values. Either you have no data because it's cloud. You can see you have sometimes a lot of cloud, or you can see you have an indication it's either water, but it's normal that it's water because it's the ocean, or if it's flooded or not. Okay. So if you want to follow along, so these are the package that we are using in this example, and so I'm using now just 2 different tiles, which are here, and here we essentially downloading the data. Okay. So again, we have the URLs is a list of URLs, and we want to extract the name. So this part of an URL, okay. And it's quite convenient that in Julia you can just say base name, so extracting the last part of an URL, dot a list of URLs. So you automatically applying this function to all elements, so you don't need to write a for. And similarly, if you download a whole list of URLs, you just say dot download dot and then the list of URLs and then with the corresponding list of files. So doing it for a large number of URLs is simply just the same as downloading a single URL, but you're applying the broadcasted version of the function download dot something. Okay. And we can then expect the first GeoStiff image, and it's structured a bit like in a CDF file. So we are the GeoStiff is a two-dimensional data set, so rows, columns, and it's quite high dimensional. So it's 4,800 by 4,800. And you have the data variable, which is called band1 in this GeoTIFF file, and it corresponds to near real-time combined Terra and Aqua Modis flood data. Okay. You have also, but in addition to this, you have also some metadata. You have the projection, you have X and Y coordinates, and also the longitude latitude. Here, the longitude latitude actually correspond to exactly to the X and Y variable, but it doesn't have to be necessarily the case, because sometimes you have grids which are tilted relative to the X and Y direction. So that's the reason why in general, lone lat can be a two-dimensional array if this is tilted. But in GeoTIFF, these arrays are only materialized, are not materialized in memory. They're only virtual arrays, so it does not really take that many memory in your CPU. It's just a virtual array, and all the elements are actually computed on the fly when you need to access them using the projection. And then in GeoTIFF, you have also the flexibility to add a lot of different metadata themselves as a key value pair. And here we're using the metadata as it's stored in GDAL. So with all this additional information, particularly you can have a description attribute which tells you what actually do the different values represent. Okay, so you can query the different variables. So just by accounting size of the band1 variable, it does not load the data. It just queries the size. It gives you the size. Okay. But in our case, actually, the data is distributed in granules. Yeah. But they sometimes when you are interested in data which spans different granules, it is quite useful to concatenate them. Okay. And this you can do also in TIFF datasets. It has multi-file support, so meaning that the dataset can actually span over different files, and you just aggregate them virtually along a given dimension, which is here the dimension. And if we do that, we see that indeed the first dimension is not twice as large because we just lumped two dimensions together. Okay, and then we can index this array by using numbers, indices, or we can actually load the data set by using longitude and latitudes with the select macro, and we can then so once you select it, so we can either select a single variable or a whole data set. So if you apply this to the whole data set, also longitude latitude
Alexander? Yeah, I think his image just froze. Just let's wait a few seconds to allow him to join again. We still have time. So, Alexander, I again.
Yeah, I'm sorry. I think my internet connection dropped for maybe
Yeah.
I
And
don't
maybe it's better if you switch off your camera. Probably it'd be
Oh yeah, let's do that.
okay.
Stop video. Okay. Let's try again. Share my screen. Hmm. Let's try again. Share. Share. Okay. Okay. Do you see my screen again?
Yes.
Oh, okay. Okay. Oops. Okay. So yeah. So I was explaining the different operation that you can do in TIFF dataset. Selecting data based on the coordinates, and here the last thing I think where this connection dropped is where we made a plot about the data, and so this is a plot made with Maki, and which is a very efficient library for making plots. So I use Python plot, PyPlots quite a lot, but GeoMaki, even is syntax not too familiar for me, it's really efficient. It's really fast. It just takes a bit longer to install. But here is one plot that you can make with GeoMaki. So where you can plot this raster using the categorical labels, meaning 0, 1, 2, 3, which corresponds to no data or 3 flooded data. So here, what you see here in red is the area that was flooded during these extreme precipitation events. Okay, and I'm almost done actually. So the JuliaGeo community is actually quite active, and I was looking what is the oldest package that we have in JuliaGeo, and it was, I think it's called the NASAPrecipitation.jl package developed by Fabian Jans, and was even the first commit was done in November 2012, which is quite astonishing because it predates the release of Julia 0.1, and and so yeah, it is a quite active community. Not all packages are maybe developed initially on the JuliaGeo organization. Sometimes packages are transitioned there or developed outside. And I showed you some example of application of grouping and reduction operation available in common data model, but they are also accessible to they're not only accessible to NetCDF, but also accessible to RIP dataset by Tristan Carrion, ZAR dataset, and then TIFF dataset. And another thing that was developed was another operation was rolling groups. If you want to make a let's say a 10-day average or a weekly average, but over a rolling time frame, that's also something that you can do, which is done very similarly to the group operation, and it's quite easy to add another reduction operation. And NC datasets and GRIP datasets and ZAR datasets, for example, also integrated into rasters, which are also quite quite commonly used package for these operations. And I want to also give you the link of the Julia forum, which is a discourse forum, and there is a section called Geo. And if you have any questions, really don't hesitate to go to this JuliaGeo section, which is very. There are a lot of people who are really active, and even for me, I'm not that active on this forum, but I think it's very interesting just reading the different packages announcement and different development that has been done in the Julia ecosystem. So it's really a great resource that I really recommend you to checking out. Thank you. That's all for me.
Can you stop sharing? Okay. Hi, Alexander. I think there's a question for you in the Q&A. We have one. Can you hear me? We have a question from Alan Rosales. He asks, what is the resolution of the coastline that you can plot in Julia using this package? Can you hear me, Alexander? I think he can hear me. Alexander? Well, we can answer this question at the end of the presentation. So we are a little ahead of time. But we're gonna keep it. Go ahead, Felix. You wanna say something?
Yeah, I had a question for Alexander.
Yeah, but
he's not here anymore, or?
Yes, hi, Alexander. Yeah.
Hello.
Hi.
I think Zoom crashed on me.
Do you see some questions in the Q&A? Can you answer them? Because there are some technical parts that I don't even know how to pronounce it. So if you can help.
I just need to find the Q&A part.
It's on dashboard below this. No. Felix, can you help here? Can you read the questions in the Q&A?
I can read one of the. So one question was, what's the resolution you could plot with the land sea mask data that you get from your packages?
Oh, great question. I have to check Geo data set. So the resolution which is integrated, the land sea mask. So the land sea mask. Okay, I have it here.
It's 1.25 minutes, arc minutes, right? At least that's what the documentation says.
Yeah, exactly. Great. Yeah, that's the finest resolution. Yeah, 1.25, that's the finest resolution. Yeah, exactly. And there are different resolution as well, but that's the finest. Exactly. Thank you.
And then the next question was, what is the best package to plot netcdf datasets? For example, to plot temperature and overlay streamline, wind, vector, etc.
Good questions. In the Julia ecosystem, you have different packages for plotting. So I used to use PyPlot a lot because it's I used MATLAB before and Python before, Matplotlib before, so it was a very familiar syntax. But I noticed that Maki is so much faster. It's so much faster. So and the syntax might not be that familiar if you're having a similar background than me. But I see a lot of people moving towards Maki. So if you are new and if you don't have any prior Python experience, so I would definitely recommend you to look at Maki. And even if you use Matplotlib before, it's not that different. It's just I would recommend Maki.
Then I also would have a question regarding this group by. Did you look at the? I mean, there was a group by added to dimensional data as well recently. So what's the difference between doing it in common data model and doing it in dimensional data?
Actually, when I started to implement it, I don't think there was already a group by in rasters, but or maybe I didn't see it. So I think there is some overlap in functionality there. So I really cannot say exactly what kind of what we're doing differently. So
Okay.
I don't know, but yeah, it's definitely something quite interesting to check. I don't know, maybe you know this better than me. Are you doing some broadcasting operation in or maybe you know this, Felix, if there are some broadcasting operation in dimensional data when you do a group by operation?
In the group, I don't know. I'm not too familiar with the group by in dimensional data because I didn't needed it yet, so I hadn't looked into it yet. But I think there's also broadcasting, and I just think that it would be good to streamline this and have some common implementation that can be used by any
Yeah,
package in the end, right?
yeah, that would be good indeed. Yeah, for sure.
Okay. If there's no more questions, well, I think we're ahead of time, but I think we can go to the next presentation. What do you think? Instead of the making a break for you, Felix, for you, it's okay? Yeah. Okay, just
I would have take a 30-second or so break to get a glass of water, but then.
Okay, no, we can skip the break. We return in half an hour because it's to keep with the schedule. Or
No,
you can.
That's for you to decide. I don't know. I mean, I could also just continue.
Okay, but you can get a glass of water. It's fine.
Yeah, I get a glass of water and then I
This is
continue.
informal. It's fine. It's informal session, so it's fine.
Did we cover all the Q&A questions?
Yes, yes.
Okay, great.
But the attendees can put more questions and we can address them at the end if necessary.
And the participant, can they speak directly or they have to
that's one thing we can ask attendees if they want to speak. They just need to raise their hands and I allow them to speak and they can put questions directly to you instead of writing them on the Q&A. Okay, so Felix, you're the next speaker. If you can introduce yourself, would be great.
Yes.
Okay.
Yeah. So let me just share my screen. That is that one. Yes. So yeah. Hi everyone. It's really nice to be here and to be part of this workshop on Julia. And so my name is Felix Cremer. I'm currently working at the Max Planck Institute for Biogeochemistry in Jena in Germany, where I'm doing some parts on change detection using Sentinel-1, but also doing a lot of package development in the Julia geospatial ecosystem, so to say. And so if there's anything that is unclear or you want to have it explained a bit better, then feel free to just stop me and or write the questions into the chat. So I'm going to talk about change detection in Sentinel-1 time series with Julia a bit, but I'm also going to talk a bit more about how we use the JaxArrays package, and also I'm going to talk a bit about the ecosystem on plotting. So a bit about, I'm going to start with Sentinel-1 data, so that we know, so then a bit on change detection and on how we implement this in Julia, and then also I'm going to talk about the pyramid scheme package that we're using to plot very large geospatial data interactively. So I'm first going to talk about synthetic aperture radar, which is the technology behind the Sentinel-1 satellite. So Sentinel-1 was launched in 2014, the Sentinel-1A and Sentinel-1B in 2015, and so we have a lot of data available. So from mainly on land area, but a bit on sea ice and a bit of basically everywhere. But of course, since it's a European satellite, it's a bit focused on Europe, but also in other areas of the world, you have a quite good temporal coverage. So from at least 250 scenes up to more than 1,000 scenes per area. And so what is Sentinel-1 is a so-called synthetic aperture radar. So it's a side-looking radar sensor. So basically the satellite flies by and then takes with a certain angle. It sends an image out, it sends a signal out, and it looks at what is returned to then capture some information of the Earth's surface. So and what is going on. So for that, so therefore, since it's an active sensor, it's very nice because it's not as hindered by cloud and atmospheric distortions as the optical sensors like Sentinel-2 or MODIS. And but we have to understand a bit what we're looking at, because it's not like, I have the feeling that for optical data, a lot of the people are more familiar with this because you're a bit used to looking at aerial images from Google Maps or from other sources. But with SAR, you have to bit understand what is happening. So since you have this active sensor, so you have this in black, you have the signal coming from the satellite. Then there's some interaction on the surface, and then you have the blue lines going back. And then you can have either this so-called double bounce, where it goes to some vertical structure and then to the ground and then going back, or you can have surface scatter on the vegetation, or double bounce, a stronger double bounce in urban areas, or just direct scattering on the ground. And depending on that, you have differences in the signal that you would receive. And if you now look at change, you can imagine you go from this state to that state, for example, if you have a deforestation event, or you go from this particular scattering to double bounce with man-made structures, which is much higher than the scattering that you get from vegetation. And now we also want to talk, so we want to do change detection on Sentinel-1. So for that, we are starting with Sentinel-1 data on a 20 by 20 meter grid. Then we compute this RQA trend metric I'm going to explain in a minute. And then I'm mainly interested in forest maps, so I'm looking at forest areas, but that could be decided on a case-by-case basis. And then we are doing some clustering. And for this change detection, we are using this so-called recurrence plot or recurrence quantification analysis. So say you have a certain time series of a certain length, and then you want to detect some structure in it. You compare, so the recurrence plot is the idea. You compare your time series against itself, and then you go from having this time series going to having this recurrence plot where you have some structure of the data. And then this is just artificial data examples where you have some different seasonalities, or a step function with some noise, or some seasonality, but also some trend component. And these give different structures in the recurrence plot. And these are nice to look at, but to actually work with them, we want to derive information out of them or some metric out of them, because we can't look at all the recurrence plots of all the pixel of all 20 by 20 meter pixels in the world. And to do that, we could compute the so-called accurate trend. So the idea is we have here, so this is the so-called tau recurrence. So you have on a recurrence plot, you have the main diagonal, which is every point against itself, and this is always, of course, it's always the black line because every point is similar to itself. And then, but then you can go for every line, you can basically count the number of similarities on this diagonal. So basically, and then you get a value compared to, okay, how many points do I have on this diagonal and how many are considered similar? And then, so you go from counting this line, you get this value, and then you do this on these different examples. And then, since this tau recurrence is now you can do a regression of, okay, is there some trend here? Because basically the idea is, does the similarity of two points depend on how distant they are in time? And so we take these lines and then we say, okay, the trend metric that we're going to look at is the slope of this yellow line. And this was just now artificial examples, and now we can also look at actual examples. So this is from examples in central Mexico. So here on the left we have a deforestation event. So there's a clear cut in the forest area that we saw using high resolution optical images, and then you see, okay, there's some definite change here going on at this point that you may or may not see in the actual time series of Sentinel-1, because then there's some drop, but then also at a later time there's some returnment of the backscatter signal to the previous values, and then and on the stable forest you have basically the same or more or less the same backscatter values all for the whole time. And then if we computed this accurate trend, we saw that for the areas that are clear-cutted, there's a strong signal in this accurate trend that overlaps quite nicely with the actual areas of deforestation. And now, why is this not working anymore? Okay, and now we can have a look at, so we're currently computing this for Europe. So this is a map of Europe for this accurate trend, and so I would say forest change data. And so unfortunately my background map is not loading if I'm also using Zoom at the same time. But like this is the Harz Mountain range in Germany, where you have quite some deforestation or forest change due to bark beetle and drought-induced diebacks, and then also if we could try to go to Portugal. So here, there are certain patterns in the data which are still artifacts of the computations that I'm hoping to get rid of in the near future. But also here in Portugal, you have some deforestation events, and then yeah, you can basically plot this as a so next steps for me are also analyzing this, and but for now, I would say this is what I wanted to talk about change detection. Are there any questions regarding that? Let's see. If not, I would also now explain a bit why, or still have some time, right? How we can basically how we do this in or how I'm working in Julia. So as Alexander said, we have this ecosystem, and so I'm mainly working with ZAR data and not with NetCDF data, but then I'm mainly working with this JuliaGeo package, which is a slightly different approach to so it's similar to the rasters.jl package, but because it's also building on dimensional data, it has a much higher focus on larger than memory out of memory arrays, so it's much more lazy and tries to never print any data that if you don't want to actually use it, because data access might be very slow if you're working, for example, on remote data sets. And the JuliaGeo package introduces the so-called mapcube function, which is like an extended version of a map slices, where you can define artificial, or you can basically define very complicated input and output structures. So say you can map one large data set, do some slicing, and then output two data sets, or you can combine multiple data sets, and then JuliaGeo is going to take care that this is is going to be efficient from a accessing pattern point of view, so that you don't run into this problem that your data is opened multiple times because you want your time series, but then your data is only available as maps, and then you basically have to open it all the time, or you can and then it also automatically is going to parallelize your computations either on a distributed way or on threaded, depending on which computational resources you are going to give your data. So I think I'm not going to go through all of this because we might not have the time, so I'm going on not in detail, but if you're interested in, we also recently did a data cubes in Julia workshop, where you would also find these materials online. I can also add the link later to the chat. But yeah, so this mapcube function is like, yeah, so you first load the packages, and then you open your data, and then you can like this is now following this dimensional data syntax of, okay, you can just index here with this latitude equals, and then you can decide, okay, near 11, or also between would work, or all these other nice things. And then, as I said, we have this mapcube function where you would just apply your function like you could just define it on one dimension. So you have this, you define the inputs as indims, and then you say, okay, I want to have this on the latitude. And then your function needs to always take has to have a certain structure where you first as the first variable is your output, and then your input, because then you can basically insert your result into the output. So this output variable can be pre-allocated, so it would be faster. And so here we just compute the median on all non-missing, non-none values of your data. And then here you apply this function with using mapcube. So you have you say, okay, mapcube, and then you add the function, and then you say, okay, this is the data set or data cube that I want to apply it on, and then you define the input dimensions and the output dimensions. And now we can also plot it. Then we also have map, which just applies the function on all elements, just so that you, for example, here add 273 to go from Celsius to Kelvin degree, and this map will then be applied lazily, so it's basically pre-registered, and then it's going to be applied once you do something else on this. So, for example, if you would plot it, this computation that you pre-registered before is also going to be applied. And then you can also sometimes in your inner function you want to have some other some additional variable that is not coming directly from the data, but is something that you want to add as well. So we can just add these as well, or you can, as I said, you can just combine multiple outputs. So here we have multiple outputs and one input. And then we compute basically the mean, the standard deviation, and some normalization, normalized time series. And then, and here you see that the input is one dimension, and the output is, so you have multiple output Q data sets, and then your outdims is a tuple of these different output dimensions. They say, okay, and then you can also just save it somewhere and keep it for later, so to say. And what also comes quite handy at sometimes is you can apply functions not only on slices of your data, but also on moving windows. So you can say, okay, I take the mean. I mean, I filter for missing here, and if the inner element is missing, then it is going to still be missing, and then here you define the input dimensions as, okay, indims of, and then you say, okay, I want to have a moving window of latitude and one before and one after my time, my position on the grid, and then we now, like here, and then you could make this longer, or you could could also, if you want to have a if you have a time dimension, it might make sense to say, okay, this is 0 in one dimension and 7 in the other, because you're not interested in looking ahead of your actual time, but only at in the history of your data to make certain predictions, for example. And then you apply it just normally. And is there anything? Yeah, let me just solve. And then one last thing I wanted to at least mention here is that you're not restricted to using Julia functionality in here. So you could also just say, okay, I want to have some Python function or some R function that I really need, but I want to apply it on a larger grid. And then you can just use this Python call or R call package to load it, and then basically use something here in the inner function, and this would just work. And then I'm also just going to quickly talk about this. Is, as I said before, is you have this easy parallelization where you can just say, okay, I either started my Julia process with threading, or I'm going to use distributed and add procs. And you can also just use this on cluster managers like Slurm or others. And then you just have to make sure to load your packages on all your workers. And then you can, if you now would run a mapcube function, this would just take all the resources that your Julia process knows about, and thereby parallelizes it. Are there any questions on that, or should I just go ahead and show you how we? Alex, please.
Yeah, I have a quick question. It's really interesting,
Yes.
your parallelization work here. I'm just wondering if you have based your if you are based on Dagger, or do you use your own parallelization strategies?
So JuliaGeo is currently using its own parallelization strategies, but Fabian is also working on DrWatson engine,
Okay.
which is basically trying to take what we learned from the work on JuliaGeo and make it nicer, or make it more, generalize it a bit, and also make more lazy computations. And I think there's also some work on a Dagger runner that would then, at least some of the parts would then also use Dagger in the background.
Okay, interesting. Thank you.
Yeah, then okay, it's not run anymore, so I have to decide whether I'm going to, yeah, I'm going to do it live. So the last thing I wanted to talk about today is this package called Pyramid Scheme. So it's what I'm currently working a lot on is it's a package for basically nicely and efficiently working with very large data sets. So say 100-meter resolution global above ground biomass. So this is data that is definitely to put, it might fit into your RAM depending on your computer, but it's definitely too large to fit onto your screen, because it's 400,000 by 200,000 or so pixels. And therefore, if you want to nicely work with that, you need to be a bit smart in how you access this and how you try to do this. So what we do here is we can just load a package and then we load some additional things like this. We just say, okay, the longitude is an X dimension and let is a Y dimension, and then we can load this data, and then this is now a ZAR data set that is living on our min.io, but that has these so-called permits. So what is a permit is, so the idea is that since you can't plot the whole data set onto your screen, you take your data set and then you aggregate the data by, by always taking 2 by 2 pixels, aggregating to a new value, then taking another 2 by 2 pixels on the coarser resolution, and so on. So you go from very high resolution to very coarse resolution and thereby decreasing the size of your data. And that's why it's called a permit. And you do this until you get to a stage where you can actually fit the data that you would end up with onto the screen. And for example, TIFF already has this. So in TIFF, this is called overviews, where you basically always have your 2 dimensions, and then you can add these to your TIFF to get faster access to the data. And in ZAR, there's currently discussion on how this should be done. In NetCDF, for example, I don't know whether there's anything that could be done there. And so permit scheme has a functionality to actually compute these things by just doing permit of, no, wait, I have to, let me just quickly show you the example. So here we would take some raster data, and then you could you open it as a data cube from Yaxarrays, and then you can just save it, and then you can just do this build permits function on it, and then in build permits you could also decide which aggregation function to use. So for some data sets, it would make sense to take the mean. In others, it might make sense to take the minimum or the maximum or some median, or I don't know. I mean, that depends on the actual data that you're looking at. And then and then once you have that, you can go ahead, and then you would end up with this the structure. So you see you have these 11 levels, so going from 400,000 by 57,000 pixels up to this very coarse resolution 198 by 77 pixels. Always decreasing the resolution by a factor of 2 in both dimensions. And this is an abstract dim array, so you can more or less work on it like you would with other kinds of dimensional data arrays. And then so we now loaded this, and then we can just do, let me just reload the data so that I'm loading it locally, so it's not going to crash my computer again. And now if we plot this, you see that you have the, so this is above ground biomass from 2020. And now if we zoom in here, maybe we zoom into the Amazon, where we would see these fishbone patterns, and then you see the increase in your in the resolution. And now we are not only interested in a certain, in one data set, say, or because we also have the data for 2017. And now we say, okay, yeah, I mean, we can still zoom into the same, but did there something change? I don't know. I can't, I mean, I forgot what the other one looked like. So we want to do the difference. So we just take the difference between 2017 and 2020. So this is also, this is applied lazily now. So it's just this broadcasting operation. So it's applied on every element, but it's basically applied on every element on every level of your pyramid. And therefore, you can now just do, okay, we plot this now. Let me fix the color bar again. And then if you would do this kind of element-wise computation on this data set, which is, since it's only one time, or basically 2 time steps, but is not that large, but at least on my computer, this would take at least an hour or longer. And now you would get the actual information immediately. And now you can basically, you can plot into some areas and say, okay, is there something happening here? Or there's some increases in the green one is decrease because it's the other way around. Just realized, maybe I just quickly fix that. Yeah, and then you can just zoom in and out, and because it's applying the function only on the data that you just need to plot at the moment, because that's the only part of the data that you will see on your screen. This feels very interactive, or is very interactive, because you don't have to wait for all the other data that is, all the high resolution data that is underneath it on the whole world. You just plot the data that is actually interesting to you at this moment. And of course, depending on the computations you do, this might be slightly off to first taking the data or the computation for the whole high resolution data set and then doing the aggregation, but at least to get a first glimpse of, is the computation doing what I wanted to have? I think this is very useful. And we also work now on, so our next step on doing that is maybe looking into other dimensions. So permitting also time dimension, for example. And also we looked at hosting this, so having a server that can do tile provider, so you could get an XYZ tile from any data set you have or you would like to look at, that you can then integrate into some web applications to quickly look at the data from some browser. And yeah, that's what I wanted to talk about today. I think I'm done and happy to answer any questions.
I think you have questions in Q&A.
Yeah, let me find it. Yeah. So to Alan's question, is there a special package to plot radar data? So for this, I think there's nothing special about radar data plotting wise. So I'm a heavy user of Maki because I really like the interactivity, and I think you can quite quickly integrate, or you set up some dashboard that you could run on your local machine. Yeah. And I'm not sure what you mean by interpolate. Maybe you can also add to that question. Maybe you can also get the mic.
Go ahead, Alan. You can speak.
Thank you.
Thank
Yeah.
you, Felix. Thank you, Felix, for your presentation.
Wait, Adriana, there's Alan is going to speak with Felix. I
Okay.
gave you permission
Yeah.
to speak. Okay.
Sorry for interaction. My second question was related to, I mean, after you're using radar data, how you can compare that with, for example, with some model output. If there is a special package in Julia to do that, or yeah, basically it's my question. Thank you.
Yeah, there's no special package for that yet. Or I mean, I also don't think that we need one, because I think the hardest part of that would be to bring the radar data and the and your model data onto the same grid. And because as soon as that is done, you can do just your comparison element wise, or what you are interested in then. But I think for this properly regridding data, we don't have or at least I don't know a good solution yet. I mean, we have some people did some things, and it's some scripts are floating around, but nothing in a proper package with a proper user interface yet. That's my interpretation of that. Yeah, I hope that answered your question. And regarding the question by Sanusi, the Julia packages, or at least all things we are doing, or what I also presented, is open source, either in the, I mean, I think most of the things are in the Julia data cubes organization, because we currently have that. And wait, where's the chat? Then I can just paste it here. And yeah, and the things I showed should at least once in something in the Julia data cubes workshop, or either in the package documentation immediately. And I also wanted to add, I think that, so I really like Julia and working with Julia, but we are a much smaller ecosystem compared to Python and R. And I think because we're much newer, there's a lot more rough edges. And we would actually need you to help make them smooth, because for me, I sometimes feel some of these edges, but sometimes I'm just so already accustomed to it that I don't know where the problematic things are anymore. And so if there's anything that you think is not explained good, or could just be made better, just please open GitHub issues, or as Alex also said, start discussions on the discourse, because without user feedback we won't help, or it won't get better. So we would really like to get some feedback on that. Okay, thanks.
Okay, thank you, Felix, for your presentation and for all the answers. And thanks to everyone who joined us. Up next, we will have Nathanael with the 2 more presentations. We will now take a break of 13 minutes and we back soon. See you shortly. Hello again, everyone. We will now continue with Nathanael's presentation. Nathanael, could you please introduce yourself and begin whenever you are ready?
Hi, can everybody hear me?
Yes.
Hi everyone. Okay, let me start sharing the screen-ish. Okay. Um, Here's the screen, share the screen. This one. Yeah, let's share this one. Okay. Okay, so morning everyone, or afternoon or evening, depending on where you are. I'm currently a PhD candidate studying climate dynamics, and I currently use Julia in my line of work to extract and subset and analyze gridded data sets such as the NASA GPM dataset for rainfall. And I also use it to analyze reanalysis data sets such as ERA5. So today, my presentation is today I'm going to do two presentations. The first presentation will be about the packages that I've used in order to do my extract downloading, extraction, and analysis, part of the GeoRegions ecosystem, which I hope that you can see from the slides. My slides are visible, right? I hope my slides are visible. The GeoRegions ecosystem. And then the second part will be how I have used various Julia tools such as DrWatson and Pluto notebooks in order to help me in my projects. As a disclaimer, I am in charge. I'm the one who created and maintains the packages that you will see in the first project, which is the first presentation, which is the GeoRegions ecosystem. But I'm not the maintainer of Dr. Watson or Pluto notebooks, which I will be talking about in the second section. I'm just going to talk about them as tools that I have used to help me in my project work. So the first presentation, which is on the GeoRegions ecosystem in Julia. So basically today what I want to do for this first presentation is I'm going to talk a bit about three packages. I'm going to talk about GeoRegions.jl. I'm going to be showing some examples on NASA precipitation and some coding samples and examples on NASA precipitation ERA5 reanalysis. And then I'm also going to talk about I'm also going to show you guys some examples about the GeoRegions ecosystem as well. So basically what I want to say is that GeoRegions, which I coin as a short form for geographic reasons, they're meant as an easy way to specify geographic regions for extraction and analysis. So these packages and the subset packages that you see here are developed for my own research work. So while they are comprehensive in terms of the data extraction and manipulation, or at least I hope they are, when it comes to the parts of downloading data sets, say from NASA iMerge or from ERA5 or from other data sets, these other data sets, handling of those data sets in the sense that how you retrieve those data sets, how you download those data sets will very much be dependent from person to person. So if you have a use case of GeoRegions.jl that you would like, for example, say you want to do it for Mara2 reanalysis, or maybe you'd want to do it for SAR imaging, for example. Those could be extensions of the GeoRegions ecosystem, but because they're not necessarily in my current line of work, or they're not part of my current project, I do not have packages for those other data sets that I do not use, but you can use GeoRegions for those other data sets. So the reason why I developed GeoRegions is because data is often provided in global data sets, so you need to extract the relevant data. So for example, in this figure, which I created using GeoRegions, which I partially extracted the data from using GeoRegions.jl. So basically, this is a topographic map from the eTopo dataset, eTopo topographic dataset. So what happens is that the global data set is given in the whitewashed colors that you see, but you will notice that there's this tilted region over here, which is an example of how I use GeoRegions.jl to extract a region of interest from a global data set for plotting or for analysis or example, like this is an example of a use case of GeoRegions.jl, for example. So just a bit of background. In the past, GeoRegions.jl used to be part of the Julia Climate ecosystem and organization, but I found that the Julia Climate ecosystem and organization is the Julia Climate ecosystem organization was slightly separate from what I wanted to do. So I pulled out all my packages that rely on GeoRegions.jl into its own organization, which you can find on GitHub. So if you look at GitHub, so if you go to github.com, you should be able to see the GeoRegions ecosystem organization here. So these are where all these are the packages starting from GeoRegions.jl that these contains GeoRegions.jl and the packages that depend on GeoRegions.jl, for example, NASA precipitation and ERA 5 reanalysis. So GeoRegions.jl acts as the base of the ecosystem. So this one allows for specification of regions, which is particularly useful, I have found, for certain online datasets. So for example, NASA often stores its netcdf files on the OpenDARP servers. So you can use GeoRegions.jl to specify, for example, your region boundaries, and then you can automatically extract and subset and extract the data directly from online, so you don't have to download everything and then extract and then delete the temporary file. So that's if you have a file that's online, you can use GeoRegions.jl to automatically subset, or rather, if you know how to do that, you can use GeoRegions.jl or NC datasets to specify where your data starts and stops, and then you can extract it. Otherwise, then the best practice is just to download the global data set. You extract the relevant region of interest, and then you delete the temporary, and then you delete the global data set that you temporarily downloaded for the extraction. So currently, the GeoRegions ecosystem that I'm going to present today is based on GeoRegions version 6, which is GeoRegions version 6, which is where NASA precipitation and ERA 5 reanalysis also use. So currently, the versions of NASA precipitation and ERA 5 reanalysis, they use GeoRegions version 6. I hope to update this in the future because currently GeoRegions, I recently updated to version 7. So in GeoRegions version 7, I split the GeoRegions package into three different packages. Initially, all these 3 different packages were contained in GeoRegions version 6. But I wanted to make all the individual packages a bit more lightweight, so for people to use more easily. And I will eventually update NASA precipitation and ERA 5 reanalysis to accommodate GeoRegions version 7 and the new packages region grids and landsea.jl, which are currently part of GeoRegions version 6. But in version 7, they are pulled onto their own separate packages. And I think that, and what I have planned is that eventually I will as I start using more NASA datasets such as MERA 2 reanalysis and the NASA brightness temperature dataset, which is used for clouds, so the detection of clouds basically, I'm hoping that I can put up some more packages as examples of how you can use the GeoRegions ecosystem. So that's the current state of things for the GeoRegions ecosystem and what I planned. So currently, what I'm going to talk today again is about GeoRegions version 6, and then NASA precipitation and ERA 5 reanalysis. So GeoRegions, as an example for GeoRegions.jl, it currently deals with gridded data and preferably currently deals with rectilinear grid. So if you have a longitude and latitude grid that is rectilinear, so your point, so it's basically a rectangle on the longitude and latitude grids. With the GeoRegions.jl, you could specify a region ID identification, you have a name, and then you specify the parent region, which by default is the global region, although you can also specify as another region that is larger than the current GeoRegion you want to specify. And what you will need are either your north, south, east, west coordinates, or if you want something that is, so if you use a north, south, east, west coordinates, you will specify a rectangular region. Or if you want to specify a shape in particular, what you need to do is you need to specify two vectors. One is for longitude and one is for latitude. And these vectors will then specify a shape. For example, here in the here you see the Indian subcontinent region. This is the Indian subcontinent region as specified in the IPCC 6 boundaries. For this, so basically you specify the longitude and latitude points of all the vertices or the corners, and then it will give you the respective shape. And then you can use this, for example, to download GPM iMerge data from OpenDub. And if you download, for example, NASA data, what it will download is it will download all the points in blue. Well, it will download a rectangular grid that is of this size in red, or in the blue and the red. But what happens is that the red points will be set to NAN, not a number, and then it will retain the values for all the blue points. So this will allow you for some for easier analysis. So if you want to say get the mean of precipitation for this region or mean of some value for this region, all you need to do is that this is an array, so all you need to do is take out all the NAN elements from the array and then do the mean. So that's how I have streamlined the workflow for GeoRegions.jl, and I hope that it will be useful in certain aspects for your work when it comes to Earth observations and when it comes to data extraction for Earth observations specifically. Yeah. And okay, so based on GeoRegions.jl, I have created two main packages for my own use, but they also can be used for other purposes. They're all publicly available and they've been registered on the Julia registry. These are NASA Precipitation dataset, the NASAPrecipitation.jl, and ERA 5 reanalysis. So for NASA Precipitation, it specifically deals with the GPM iMerge and the TRIM data that is hosted by NASA. NASAPrecipitation.jl. So basically, NASA for iMerge and for TRIM, they have many different data sets for precipitation. They have the hourly data set, they have the daily data set, the monthly data set. NASAPrecipitation.jl deals with all of them. The level 3 products specifically, I don't really use level 1 or level 2 products, so I haven't geared NASA Precipitation towards downloading those. But most people use the level 3 dataset, which is the gridded dataset, the global gridded dataset, the merged dataset for global precipitation. NASAPrecipitation.jl deals with all these global gridded datasets. And again, it's paired with GeoRegions.jl in order to be able to specify geographic regions of interest, so you don't have to download the data for the whole globe which can be quite intensive in terms of disk space usage. So that being said, NASAPrecipitation.jl also does require you to register on OpenDub servers. And if you go to the website, but if you go to the package website for NASAPrecipitation.jl, so sorry, this one is a bit outdated. If you go to, so this one is GeoRegions.jl, GeoRegions ecosystem. If you go, the documentation for NASA Precipitation will walk you through step by steps on how to download, how to register on OpenDub and download and what you need in order to be able to download the data sets from the NASA servers. Examples of what you can do for NASA precipitation is that you can do analysis, you can do smoothing using NASAPrecipitation.jl. So you can do spatial and temporal smoothing. So you can say smooth it from 0. Because the default is 0.1 by 0.1. You can, for example, keep it at the 0.1 by 0.1, but you smooth it over 0.5 by 0.5 by 0.5, and I'll show you an example later. Or you can also do some extraction of data sets from your existing data set. So if, for example, you've already downloaded, say, data for, say, the Indian subcontinent region, if you're interested in, for example, here you've downloaded the data set for the subcontinent region over here. If you say you're interested, say, specifically in Bangladesh, for example, over here, you can then use GeoRegions.jl to further extract data for Bangladesh from the Indian subcontinent region, just as an example. So that's for NASAPrecipitation.jl. For ERA5 reanalysis, downloads reanalysis data directly from ECMWF, so hourly and monthly data sets. And also recently I've updated ERA5 reanalysis such that it has the variable list for all the single level variables on the climate data store, which was no mean feat because it was basically specifying there are basically, I think, over 100 single level variables in the climate data store for ERA5. So again, it's paired with GeoRegions.jl in order to specify regions of interest. And it will download a rectilinear area, so it will download a long-leg grid based on the boundaries on the north, south, east, west boundaries of your georegion. So again, similar to NASAPrecipitation.jl, you can do some analysis and manipulation on the dataset using ERA5 reanalysis. And on top of, for example, smoothing and further extraction of data using GeoRegions, you can also calculate, for example, custom variables such as eddy kinetic energy, which is useful for mid-latitude storms. And a lot of people, for example, also don't necessarily need the hourly data. What people generally prefer is the daily data. So on ERA5, the climate data store, they used to only have hourly and monthly data sets. So ERA5 reanalysis provided its own function whereby if you downloaded the hourly data set, you can then convert it into you can convert existing hourly data sets that you have on your computer or on your server into daily data sets for your own usage. So, and I just like to remind people that this presentation and the examples that I'm going to show next, because I know I've talked a lot, but we prefer to talk with, I think it's better to have examples to show people how to use NASAPrecipitation.jl and ERA5 reanalysis. So this presentation and examples contained are not a substitute for the full documentation. And for more information, I generally recommend reading through the full documentation where more detailed explanations will be found. So if you go to each project's GitHub repository, for example, you will see documentation. So doc stable and doc latest. These are the links to the documentation for my packages. And I hope that I've made them clear enough, at least for people to understand how to use these packages on a slower note, because what I'm going through today is pretty fast, and I'm going through them pretty fast, and I will run through the examples pretty fast, but they're also pretty basic examples. So the full functionality will be discussed in the documentation. So right now, what I want to do is I want to give you guys a few examples of how I use the GeoRegions ecosystem, specifically NASA precipitation and ERA5 reanalysis. So for example, I will show you some example codes on how we download iMerge version 7. I will also show you some examples of how we extract the data and how we do spatial and temporal smoothing, for example. Yeah. So for example, if when we are downloading, for example, for downloading, the function to download data is simply just download. But you need to specify the data set of interest and the georegion of interest. So for example, when you're using NASAPrecipitation.jl, for example, here in the slide, you will see that you need to specify the NASA precipitation dataset, which in this case is the final half-hourly product from iMerge, and the georegion here, which I specified as the Sumatra squall, as a region of interest, which is Sumatra squalls, which is this blue region outlined here. So let's go. So for example, let me expand this. So for example, here, in here you see that this is the region that I define SQL. I define SQL here, and what you see, and again, these are the northwest, southeast boundaries, where you specify again the northwest, southeast boundaries, and then you can use these northwest, southeast boundaries as ways to specify and extract the subregion data. So first of all, what I did is I downloaded for this SQL georegion. So if in this case, these are examples, lots of precipitation. So here you see again, you've downloaded this is the code. For example, you have the NASA precipitation dataset, you have the georegion, and then all you need to do after that is just download the NASA precipitation dataset and the georegion, for example. So if I ran this right now to download the NASA precipitation datasets. So okay. So a lot of this. So basically what happened here is that in this case, what I already have done is that I have already downloaded the dataset I've already downloaded the datasets. So because NASAPrecipitation.jl has detected that I have downloaded the datasets in this location, which because I've pre-downloaded them so that I don't have to spend half an hour. You guys don't have to spend half an hour watching this thing download. So I've already downloaded the datasets and it's detected that it's downloaded. And so because I don't overwrite the data, so it's just skipping to the next time step. So that's an example of the downloads. For example, you see here it's downloaded into this particular folder, for example. So if we go here, you see that here that I have the datasets this is the daily datasets for the January, February, and March of 2011. And that's an example of how you would download datasets in NASAPrecipitation.jl, for example. The next one that I want to show you guys is extraction. So extraction of your data. So extraction of your dataset. So for example, here, I am extracting from the bigger region, the SQL region, for a smaller region here. And what it does is that it opens this. What happens is that extract opens this, opens the files that I've already downloaded here, based on the files that I've already downloaded, and then it extracts a new region here, and then saves it separately. So for example, this is in the this is in extract.jl. So again, you see that here, this script is a bit more complicated because I added the plotting functions, but here, this is the relevant part here, where you specify a precipitation dataset. You then specify the parent georegion, geo, and then the sub-georegion, SGR over here. So basically, if you want to extract data, you extract from the NASA precipitation dataset, and you extract this sub-georegion from the parent georegion. So if you run this code, so this is data set. So let's do the 7th final hourly. You see, no, sorry. So basically what happens is that just now I deleted the previous georegion, which is SGR. And so here you already have the SQL dataset. So what I'm going to do is I'm going to run this code, and so it retrieves the region information for SQL and SGR, and then is currently doing the extraction for all of it. So here you have, for example, so here I merge final day, I merge V7 final day, and then you see that it's the SGR. You see that I've successfully extracted the data sets here. So this right now for me is 8:55 a.m. So I just again extracted the SGR region from the SQR region. And again, when you plot it with the script that I have, this is the result. So you see that if you're basically just directly extracting the SGR region, which is defined here, from the SQR region. So with NASA precipitation and also by extension ERA 5 reanalysis, you can do this kind of extraction and subsetting of the data, which is useful if you are more focused on a specific region, on a more specific region of interest out of your entire project. So if you've downloaded a data set but you for say the entire Southeast Asian region, but sometimes you just want specific stations, for example, you want it over Singapore or you want it over Jakarta, then you can specify different regions you can specify different sub-georegions in order to extract those data. And it can be useful to do this, for example, because when you are retrieving the data sets, for example, from the NASA servers or from ERA 5, sometimes you just want to retrieve a data set for a region that encompasses all your regions of interest, which doesn't necessarily have to be the globe, but it's often easy to download everything once and then perform analysis and extraction on the dataset that you've downloaded once, instead of downloading it and requesting multiple times from the same server, which can be quite a hassle when it comes to Earth observation, especially since these datasets have very high demand, so you're often put on a queue. So sometimes it's easier to just download a bigger dataset once and then extract the data that you're interested from the dataset that you have already downloaded. And then the next one that I want to talk about is smoothing. So again, here we have smoothing datasets. So you can smooth you specify just your dataset, your georegion, and then sometimes you want to specify if you want spatial smoothing or if you want temporal smoothing. And if you have spatial smoothing, what's the degree of spatial smoothing? For example, in this case, the data set for NASA precipitation is given in 0.1 by 0.1, but I wanted to smooth it out such that it smooths out for 0.5 by 0.5. So in this case, in the figure on the right, you see that it's still a 0.1 by 0.1 grid, but it's just that the data has been smoothed to 0.5 by 0.5 and it moves every 0.1. And supposedly it's supposed to smooth over a 3-hour time period. Yeah, so in this case, the smoothing is uniform smoothing, and if you and again, I have the example which you can also look at online, by the way, because all this is available online. I'll drop the links to it later. For example, if you look at smoothing, you can see that again here, this is the relevant part because everything else is just plotting. This is, for example, you just specify the data set. you specify the georegion, and then you specify whether you want spatial or temporal smoothing, and then what degrees of spatial and temporal smoothing, by longitude, by latitude, how many hours you want to smooth it by, because this is a half-hourly data set. If it's a daily data set, how many days do you want to smooth it by, for example? So this is the kind of functionality that NASA Precipitation and ERA5 have, because when I look at look at iMerge datasets and ERA5 datasets, quite often I want to do similar things such as smoothing or extraction. So that's why in NASA Precipitation and ERA5 reanalysis, quite often you will have similar functionalities. Yeah. So in this case, that's smoothing. And also, of course, if you download the data, you also have to read the data. So when you read the data, this is an extension of, I use NC datasets, which Alexander Barth, who presented just now, he was the first speaker for this talk. He also developed NCdatasets.jl. I don't know if I can't remember if he talked about it in the first presentation, but NASA Precipitation and ERA5 reanalysis both use and export NCdatasets.jl such that you can read the netcdf file the same way that you will read netcdf files using NCdatasets.jl. So for example, if you want to read a netcdf file, or you don't need to learn an entirely new way of writing code to read netcdf and netcdf files. You can just look at how it's done in NC datasets, and then work your way out from there. And in this case, for example, we multiply the precipitation by 1,800 because the data here is saved as a rate, so it's saved as precipitation rate. So because it's when it's downloaded and accumulated half-hourly. So this is half-hourly data sets, but if you specify as a rate, it's specified as per second. So in NASA precipitation, I divided the precipitation by 1,800. And so here in the precipitation, if you want the total precipitation accumulation, you have to multiply it by 1,800 for that specific time period. Yeah. And then next thing I want to talk about is for ERA5 reanalysis variables. So ERA5 reanalysis, again, as I've mentioned several times, is generally the same as NASAPrecipitation.jl, except that it deals with ERA5 instead of iMerge or NASA precipitation datasets. Most of the functions are very similar. So for example, when you look at downloading ERA5, it's very similar. You see that there's a dataset, and then you see there's a georegion here. But there's also the specification of a variable of interest, whether it's a single level variable, which is like a surface variable, or whether it's a pressure variable. So a variable that ERA5 has exported at multiple different pressure levels. So for example, in the single level variable and pressure variable, ERA5, for example, specifies, like, I think total cloud cover and pressure level cloud cover with the same ID. So they use CC in your netcdf files. When you extract the variable, the variable identifier is CC, which in single variable denotes total cloud cover, and in pressure variable denotes cloud cover at that specific pressure. So so that's why in ERA5 reanalysis, sometimes I also have to specify the difference between a single level variable and a pressure level variable in order to be able to more accurately specify our variable of interest that we want to download, because again, downloading all the variables would be very time consuming and expensive. So you want to specify a variable of interest in order to download it. So again, this is how you would download. Very simple. The function name is just download. I keep it as simple as possible in general, so people can pick it up as quickly as possible. And then lastly, of course, the conversion of ERA5 hourly to daily data sets. So again, until recently, by recently I mean until October of this year. Until October of this year, ERA5 only provided hourly and monthly outputs. So because they only provided hourly and monthly outputs, a lot of people are not interested necessarily in hourly outputs. They're more interested in daily variability. So especially since the hourly output means that you're multiplying the amount of data that you have by 24. So what happened is that for ERA5 reanalysis, I also provided here in hourly to daily, I provided a way that you can convert your hourly statistics into daily average statistics. Of course, based on the UTC date line. So basically from 0 to 2359 of the UTC days. So the UTC standard time from 0 to 2359. But I think ERA5 reanalysis also recently updated itself, or rather ECNWF updated the current data store such that now it also has ERA5 you can directly request daily statistics from the current data store, and that's something that I will eventually look into and will probably update in ERA5 reanalysis. But for now, if you want to download ERA5 datasets, I offer only the hourly and the monthly option, but from the hourly option, you can convert it to a daily dataset for your usage. And that's more or less the examples and the stuff that I wanted to cover for the GeoRegions ecosystem. And if you want to, if you guys are interested in some of the packages that I've talked about here, I encourage you to check out the documentation and the notebooks. And I have also uploaded some of the examples that I just presented to you in this presentation online as well. I would encourage you guys to check that out and explore it in your own time. Also, just to note that there are some major changes that will be coming in the next few months, because I've already updated GeoRegions to so basically all the examples right now are dependent on GeoRegions version 6. I'm going to update ERA5 reanalysis and NASA precipitation to work with GeoRegions version 7 and above. And when it does, well, it's just stuff that I will be updating in these two packages, NASA precipitation and ERA5 reanalysis, under the hood. But in GeoRegions.jl itself, there have been some major rework. So I encourage you guys to look at the documentation for GeoRegions.jl, and let me know if you have any questions about it. And if you want to make some suggestions, you can make suggestions as well. You can make a pull request, for example. And of course, I also welcome contributions from people who want to use GeoRegions.jl and the entire ecosystem to download and extract data sets from other sources as well. For example, MERA2, which is something that I've been thinking about but haven't had time to do. There's other reanalysis data sets out there, other satellite data sets out there that I think GeoRegions.jl could prove quite useful for. So, and also if you find errors in the packages, please let me know. I'm not infallible. I sometimes do make mistakes, and I sometimes do find bugs in my own code as well. So if you find bugs in the code, please do let me know so I can fix them as quickly as possible. And with that, I come to the end of my first presentation, and I hope that what I said has been clear, and thanks for listening and bearing with me while I walk through some of the basic examples. Thank you.
Thank you, Nathanael. I think you have a question.
Okay, so Alan, yeah. So NASA precipitation can't work with MERA2 right now. MERA2 in itself will be an entirely separate package. So NASA precipitation so Mera 2 reanalysis is a package that I've been thinking about creating a package for. But I haven't gotten around to it yet because there's some tricky stuff with regards to what variables are where, because it's not as clear cut as an era 5. So for example, I think precipitation is an hourly data set, and is also a daily data set, and is also a 3 hourly data set. So it's kind of like there are many different it's slightly different from era 5 reanalysis. I'm looking into it, but I haven't figured out how best to go about it as of now. But it's something that I've been thinking about for the last year or so, but I just haven't had time to get around to it yet, if that answers your question. Yes, Felix?
Yeah, thanks for the presentation. Really cool stuff. How hard do you think would it be to integrate this, especially NASA precipitation and era 5 reanalysis with the rasters ecosystem?
I think that's something that I would be open to it. I think that's something that we probably might have to discuss in person in order to figure out the kinks, because I honestly developed all these packages somewhat separately from the rasters ecosystem. But I'm willing to try and integrate it a bit more. I've started integrating it into geometry ops, for example, and
Yeah.
Julia geometry. So I'd be willing and open to discuss this possibility, especially for I think it would be particularly useful for region grids as well.
Yeah.
So we can probably have this discussion offline, but I think I would be open to integrating it with existing ecosystems like the raster data sets. Yeah.
Yeah. Okay. Thanks.
Thank you, Nathanael. Do you prefer do a small break of 10 minutes, or do you prefer to continue right away?
Could you give me 10 minutes? Thank you very much.
Yeah, yeah. Okay, we are back in 10 minutes. Thank you. Hello, everyone. Nathanael, are you back?
Yes, I'm here.
Can you continue, please?
Yes, I can, definitely. Hang on. Share. Okay. All right. So, hi everybody. Welcome back to part 2, where I talk about packages that I have I have not been developing, but rather I'm talking about how I use these packages in my line of work. So today in this presentation, I'll be talking about 2 different packages. One is known as Dr. Watson, and the other one is known as Pluto. So again, as a disclaimer, I do not own or manage Dr. Watson or Pluto. Dr. Watson is managed by George Series, who is also a contributor to the Julia Dynamics organization. And Pluto is managed by Fons, who is quite active on the Julia Slack, I believe. And he's also quite responsive on GitHub as well. So if you go to the repository for Pluto.jl, you will see that he's quite active there because again, there's always bugs and stuff or new features that people are requesting from him when it comes to Pluto. Because again, Pluto is quite a while Pluto is quite a new innovation, it's actually come a very, very long way. And I find it might be a controversial take, but I find it more useful than Jupyter Notebooks, and I find it better in general. So what I aim to show you here in this presentation is how I use the tools and packages they have created to organize and aid in my work. So to start off, we'll talk about what Dr. Watson and Pluto.jl are, and then I will talk about how I use them together in my work and in my projects. So Dr. Watson is a package that you can use to set up repositories or folders for your projects. For me, how I use it quite often, I use it as a way to ensure project reproducibility. So for example, if I publish a paper, if I publish a paper, the project that I would upload, or the project that or if I'm doing a project, if I want to publish a paper based on that project, I would use Dr. Watson, initialize a repository specifically for that paper because it commits the project and the manifest, and that it allows for project reproducibility, because when you commit your project or your manifest in the package environment, or when you commit it to an online repository, you can use it to download and install exactly the same. Another person can use it to install and download exactly the same version of the packages that you are using. And with that, if you are given exactly the same data, initial data, you should be able to get exactly the same results when you perform your analysis. That's the theory when you use DrWatson.jl. So Dr. Watson was mostly created by George in order to be compatible with simulations from the Julia Dynamics organization, which he's a major contributor of. But while I do not personally use packages from Julia Dynamics, I still find Dr. Watson quite useful as a template organizer, and there are ways to build upon Dr. Watson for your own use. So for example, let's just do a basic example. If I'm using Dr. Watson, for example, what I can do is that I can therefore do initialize project and say test new project, for example. And then what happens is that Dr. Watson will automatically create and pre-compile a project for you that you can then use to like modify your you can then use to add packages to, or you can create different folders. So for example, here you say test new project, and then you see that here Julia has already set up a lot of stuff for you. So it's set up, for example, a data directory. It's set up a source directory, which is where you contain your functions and so on and so forth. scripts, which is where you then perform your analysis, and then it has a plots directory, a papers directory for etc., etc. And then important, it also creates and commits your project and your manifest, which and these two items here, these two items, the project and the manifest, are what ensures reproducibility between different computers and between different machines. And it's how I used to manage and regulate projects across different machines. So for example, if I create a project on my computer, I can then commit it to GitHub, and then I can run my and then I can download, or I can okay, so as an example, here we see that I have the Explore WTG Space project here. Here in this case, I have the Explore WTG Space project. How I use DrWatson, and later I'll show you Pluto, is that I create Explore WTG Space. I have all the for example, have all the script functions here, extract diagnostics missing. I have all the source functions here. What I have, and then this here is my remote server. This is my remote server that I use to do my analysis, to run my scripts, to run my experiments, and then analyze the data output from those experiments. So what I also have here is I also have an Explore WTG space. And then after that, you will see that, for example, the scripts are exactly the same, the source is exactly the same, and then you have that the project is also, you also have that, for example, if you compare the project is also exactly the same. So for example, here using the projects, I can ensure along with Git that my projects are synced between two different machines, and one machine on my personal computer, for example, I can modify the functions and the scripts easily using an IDE, and then I'll just push these changes to GitHub, and then from GitHub I will then pull whatever changes there are from the GitHub onto the server, and then after that I'll just pull it, and then I'll just pull it back down, for example. So that's an example of how I use DrWatson. I use DrWatson as a template organizer and as a way to easily set up my repositories. DrWatson also has a lot of useful different functions and ways to build upon the functions. So for example, if you use DrWatson, you have several different functions that you can use to specify your your data, where your data is, where your experiment is, where your plots are, for example. So by default, for example, by default, when you use DrWatson, for example, when you use DrWatson, let me activate this, and then let me using DrWatson. What happens is that DrWatson has several different built-in functions that allow you to easily express where your plots and where your experiment folders and where your source folders are, for example. So you can use these as shortcuts for your functions, for your file names, for example. So for example, here you can, if you have in your Explore WTG folder, for example, you have the run directory, for example. You have for example, the plots directory here. So if you open Julia and you're using DrWatson, you have, for example, a plots directory. And then, sorry, I need to activate the current project. So if you have a plots directory, then you will see that the plots directory is exactly this plots directory over here. So if you go into plots directory, you pwd, you see that's exactly the same. So again, but the thing about Dr. Watson is that you can use it to extend these functions. So for example, you have a project directory, which is the directory name for your folder. You can expand it with whatever custom functions that you need for, and then you can specify, for example, a parameter directory, PRM, a parameter directory, large scale forcing directory. This is for like modeling, cloud resolving modeling, climate modeling, large scale forcing, your sounding, your temperature profiles, for example. You have all these you have all these ways that you can use in order to extend Dr. Watson's functionality. So here in this case, for example, just for those of you who are not as familiar with Julia as I am, for example, here you have args and you have a triple dot. So when you have a triple dot here, it allows for an indefinite number of arguments. So you have no fixed number of argument inputs in this case. So for example, here you see there's an experiment directory and you have arguments and you have a triple dot. So you can, for example, have multiple different inputs, and then after that you can just concatenate you can just start adding up different subdirectories, for example, in order to specify different directories. So I found these basic, like what I'm showing here is relatively basic stuff, is relatively simple stuff, but I find that in a lot of times it's the simple stuff that is quite powerful, and Dr. Watson makes a lot of things for project handling and management quite simple. For example, it automatically sets up Git for you. It automatically commits your project and your manifest. It initializes the project for you. So a lot of things and it also creates a lot of different folders for you that you it's a very good way for managing and organizing the stuff that's in your projects, whether it's from data, whether it's from plots, whether it's your functions and your scripts, etc., etc. And I think that it will be I think that more people should be using it going forward for projects. It will make a lot of things more organized in general. So just a few tips. So when you use Dr. Watson, remember that one of the benefits of using Dr. Watson is that you can use Dr. Watson in order to control the version or to manage the version of the packages that you're using. So what Dr. Watson does is that you don't have to open Julia and then go into Julia and then activate the environment in order for you to load the package, in order for you to load the correct version of the package. So what Dr. Watson does is it exports this function called quick activate, where you just have to specify the project name that's in the project.toml, TOML. And then with that, you can therefore immediately activate the correct project environment and load the correct version of all the packages that you're using. So again, what I'm talking about, it requires somewhat of a basic understanding of Julia's package ecosystem. For those of you who were here for my previous talks that I conducted for the basics of package management, you should refer to those. Those lecture slides on how you can use how to use Julia's package ecosystem in order to manage package versions between different projects. With Dr. Watson, it's quite easy to activate a current project in a script, so you don't have to specify the absolute directory. You only have to specify the name of the project, and that makes it easy for you to load the correct version of your package. So for example, in your script, you have the quick activate explore WTG space, and in your project.toml, you need to have that the name equals to this project that you are specifying. So that's how you ensure synchronization between your scripts and that you're ensuring that your scripts are activating the correct project. Yeah. So again, Dr. Watson, the handling of the file system allows me to easily determine where to store my data downloads and source folders. So for example, just now, I showed you guys an example of how you can download data sets using NASAPrecipitation.jl. Another example here, where you specify that the path is just the data directory of your project. And what happens is that automatically all your stuff and with that, you can just specify that all your data goes into the data folder. For example, when you download from NASA or when you download from ERA 5, I find that again, specification of these things is very easy. So for example, you can put this script, for example, anywhere within the project folder, or you can put it in a subdirectory, you can put it in a subdirectory of a subdirectory. It doesn't matter. As long as your overarching project is, in this case here, convection isotopes, it will automatically put all the data inside the data folder for convection isotopes. That's it. You don't have to worry about absolute paths. You don't have to worry about //dots or however many subdirectories you put your scripts into. You can just put it anywhere as long as it's within the project folder. You activate using Dr. Watson, you can activate the environment, the project environment, and then it's automatically, you can specify, okay, it's just this particular data directory. That's the end of the story. Yeah. So again, this is why I find Dr. Watson very, very useful. It simplifies a lot of things. A lot of the stuff that I come in here is very basic stuff, but when I'm handling my projects and I want to keep my projects organized and I want to know where I'm at, and these kinds of basic stuff is very useful. I find it's very useful, and I hope that it will be useful for you guys too. So for example, in the source directory, in the source, you can use it to specify paths for custom GeoRegions, for example, as an example of how I use, another example of how I use Dr. Watson, where I store the functions, where I store my list of custom GeoRegions, which contain GeoRegions that are relevant to this current project, for example. So a lot of this handling is made easy by DrWatson.jl. I don't have to care where the script that contains this function is. As long as I have using Dr. Watson, I quick activate the project name, and I can just specify source directory and data directory, and that's all that I need to specify. I don't need to care about where my script is. The relative path of all these text files are relative to where I put my function. So if that has been an issue for you, Dr. Watson solves that issue for you quite easily. And I like that. So in summary, I use Dr. Watson because it's a very quick and easy way to set up your projects and the necessary directories. For example, your notebooks, your functions, etc., etc. It's also a good way to manage your package versions for your projects, and it allows you to handle folders and your paths and your directories very easily, especially when you want to specify where you want to save a figure or save your data or save your analysis or your notebook, etc., etc. Very easy. And again, it's also easily extendable for custom file systems, and in conclusion, it's just a very good way to keep your projects in general organized. And I found it to be very beneficial to me for the last 4 to 5 years, ever since I started using Dr. Watson. So that's how I manage projects. I will go into detail later on how I manage the projects with Dr. Watson and with Pluto. But for those of us who are not very familiar with Pluto, so Pluto is Julia's native alternative to a Jupyter notebook with several differences. It is reactive, so when you change a variable in Pluto, for example, you can immediately and automatically immediately automatically set the notebook to run all the all the cells that are dependent on what you've changed. So it automatically detects the cell order and the dependencies of one cell on another. So for example, in this animation here, you see that the plot below the text, the cell below plots based on what the matrix A is. And so if you change the matrix A, immediately not only do you, when you run this cell that contains the matrix A, you not only run the cell, but you also run the cell below it that depends on the matrix A. So that's an example. So Fons, who is the developer of Pluto.jl, he has a whole host of documentation. And he also has many videos that he's done with regards to Pluto.jl and how you use Pluto.jl, the benefits of using Pluto.jl and why it's better than, or I'm not sure, I wouldn't say, I don't know if he claims it's better than Jupyter Notebooks, but I think it's better than Jupyter Notebooks. So that being said, the purpose of this part isn't necessarily to show you how to use Pluto.jl, but it's rather how I personally use Pluto.jl in my projects that involve Earth observation, that involve things like quick and easy data exploration and visualization. So for example, this video here on the right is a notebook that I am using in one of my projects, for example, and basically basically it's basically it's just how I use Pluto notebooks in my projects. For example, you can see that I create plots in it, I do some analysis in it, etc., etc. I retrieve data on the servers, and then I can automate, and then I can view it on my browser, for example. It's also a way to use, it's also a way that you can use to not only just do data exploration, but if you have a project, sometimes you want to do things in a systematic way. It's also a way to craft a story, because again, if you look here, you see that you can, because Pluto.jl also supports Markdown. If you do if you are so inclined, you can write summaries, or you can write of what you found, and then you can put it on the notebook, so that when people download your notebooks, they can understand what you're doing. So in a way, you're kind of like crafting a story out of your you're crafting a story out of your what was it? You're crafting a story out of what you've done. You can use Pluto notebooks that way. So again, Pluto, and also I find Pluto similar to Jupyter notebooks. It's similar a bit to using X11 if you've used like remote. I think if you use a remote server, sometimes you can use Jupyter notebooks, and I believe that you can use Jupyter notebooks on VS Code, and sometimes if you have data on a remote server, and then you can open the remote server and then link your Jupyter notebook to the server or something. So basically with Pluto notebook, you can kind of do the same thing using your own browser. For example, here on this, I actually do most of my work on the cluster, on my university's cluster. And what I do is I just SSH and I tunnel into the server, and then I can manipulate the Pluto notebooks on my browser, and then it allows me to directly access the data that I have put on my server and analyze that data and visualize that data without needing to download any of that data. So it allows for me for quick and easy access. It saves a lot of time on downloading and data transfer, basically. So let's look at an example using my project as an example. So again, this is one of my projects, Explore W3C Space, that I will show you just now. The GitHub is also the repository is also on my GitHub. And again, all my Pluto notebooks are stored in the notebooks folder. The data is not available, but I'm just showing you an example of how I use Pluto.jl on a day-to-day basis with Dr. Watson. So for example, here I'm going to show you, let's open a pre-existing notebook. Okay, let's open a pre-existing notebook. So for example, here, where I've already opened the I've already opened the connection to my server with you. So here, this is what I see when I open Pluto on my web browser. It's tunneled from the Harvard from the university clusters. I've got several different notebooks open here because like I often work on these notebooks. I'm working on these notebooks right now on a day-to-day basis. But here, this is an example that I want to show you. This is RC spin up, which is from if you look at it's from the Explore WGG space. This is RC. So what I wanted to show you is how I combine Pluto notebooks with Dr. Watson. So when I'm using Pluto notebooks in Explore WGG space, quite often I also want to be able to load projects, or not projects, I want to load packages or the versions of packages that I am using for the Explore WGG space project. So what I do is that, so Fonz, what he did is that he now has set it by default such that a Pluto notebook has its own environment. But what I want to do is I want to activate my project environment. So doing that, what I do is I first have to activate the main environment first. So I use package, and then I activate here you see it disables Pluto's built-in package manager, and I activate the main environment first. And then from the main environment, I then use Dr. Watson. I have installed Dr. Watson on my main environment, and I use that. And then in the next cell, then I activate the project. I activate Explore WG space, and then I load all the statistics and all the stuff from I load all the statistics and all the stuff that all the packages that are part of the Explore WGG space project. And when you load, for example, a notebook that you have already created, usually what happens is that the notebook won't run automatically. This is to prevent, like, say, if you downloaded a notebook from online, this is to prevent if people have installed malware on the notebook, so it doesn't automatically run and install the malware on your computer as well. So if you trust the notebook, for example, then you run the notebook, and then now you see that all the cells example here are running. Yeah, so that's generally how so you see here, again, once the cell has finished running, then you'll see some output, for example. So this is example how you run a Pluto notebook. I'll let it run first, and then after that, we'll come back to it later, because this is just an example of how I use Pluto and Dr. Watson together. So in example, example time, let's just create a new notebook from scratch in order to explore some data in the Explore WGG space project. Shit. Did someone kill this? Looks like someone killed it by accident. Sorry. I didn't expect this. Someone accidentally closed my connection to the server. Hang on. Okay, I'm going to cancel this. Okay, so in the meantime, does anyone have any questions while I get the server set up all over again? I'm very sorry, I did not expect this. Someone killed the server while I was running. Yes, Felix.
Could we, just a quick question. Have you tried using Maki and Pluto, or?
Yes, I've tried using Maki and Pluto before. I use Maki specifically because I use Maki specifically for for when I'm doing presentation specifically, but in my day-to-day, I use other plugin packages. But yes, I have used Market on Pluto before. It's
Okay,
possible.
so the integration is much better now because I tried Pluto a few years ago in the beginning, basically, and I ran into some problems with Maki and with, I think also with our Luxware package.
It also
But
depends on it depends on which version of what version of Maki you're using. Are you using GR Maki? Because I personally use Cairo Maki.
okay, yeah, then it works. Okay,
Yeah,
that makes sense.
because
Yeah, I mainly use GL Maki because I want the interactivity.
you want the interactivity, right? I think
Yeah. But I
Fonts
mean,
is still working on. I think I've seen some examples with GR Maki before. You might want to contact Fonts for this, I think.
yeah, just whether you have. I just wanted to know whether you have hands-on experience on that. But yeah, because we have time to talk about this anyway, right?
Yeah, we do. This
Waiting for
sorry,
pre-compilation.
yes, because I also recently just reinstalled Julia version 1.11 on the server because previously the first version 1.11 was crashing on my server for some reason, so I reinstalled. Now I think the problem's been solved, so I reinstalled it again. But yeah, okay. Please let it work. Please let it work. Da 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 da. Sorry to everybody else who's in the audience. This is the downside of trying to do everything live on the server. But at least you guys get, at least for those of you who are somewhat new to Julia, you get to see how things work. So how you how you use Pluto, for example, how you the pre-compilation process, etc., etc. Yeah, it's taking a while. It's taking a while. But anyway, to not oh, has it been pre-compiled? I hope it's pre-compiled. Okay, so this is his website. For those of you who are interested and who haven't used Pluto Notebooks before, this is his website. And again, he's got lots of documentation, how to install, etc., etc., etc. I recommend looking through the documentation again as well. Oh, and it looks like it's all it's up. So okay, edit bookmark. Okay, so for those of you who are new to Pluto, whenever you run Pluto, you will always get you will always get a link that you can use, a link that you are supposed to use, and a secret, this secret here, in order to access the Pluto notebook. So I just copied and pasted it here, and I'm going to open it. Yes. Okay, so all loaded again. Very good. Okay, so let's do this again. Let's do this again. Okay. So now that we're so now again, you see I just opened the Pluto notebook again. This particular Pluto notebook. Let's run it again. Let's run it again, and then we'll just let it run because this one will take a while to run. So let's create a new Pluto notebook from scratch. In this case, let's create a new one from scratch just to give you guys an example. So in this case, okay, it's detecting. Okay, should be fine. Okay, it's running, still running. So first we start by using package and then package.activate. And then using Dr. Watson. So what happens is, okay, so let's do this notebooks. What should I name it? I shall name it example.jl. So I've moved it into the Explore WTG Space Project notebooks example. So in this case, what I'm going to do is that I'm going to run this. And then again, and then the thing about Pluto notebooks is that everything needs to be lined by all the cells need to be line by line. If there's more than one line in a cell, you need to have a begin and an end. So here, I'm using package to activate. This again means I'm activating the main environment, and then I'm loading Dr. Watson from the main environment. And then I quick activate explore WTG space. Let's use NC datasets here. And then after that, using PyCall, PyCall, plot, PyImport, ProPlot. Okay, so I'm using this ProPlot. This is this extension. This is a Python plotting package that I generally use because that I generally like. And if you guys don't know, you can actually use Python in Julia. I think Felix was mentioning some examples, showed you some examples just now, importing Python from Julia. I'm doing the same here. And then we're exploring the stuff. Okay, so explore WTG space. Let's load, for example, some data in GGW, P1 to 1, damping 0 to 0. Okay, so again, so basically using Dr. Watson, you can basically specify the data directory here. So what you're going to do is that once this is activated, I hope this activates soon. You can do NC data set. You can do NC data set data directory. And then you can just do DDW. 0 to 0, D00. Out stack. And then here, I'm just going to show you guys an example. Z equals D as Z. And then close the data set here. And then what I'm going to do is I'm going to plot the data set. I'm going to show you guys how we can do plots. Visualization. Okay. Oh, I forgot this one needs PNG files, image show. So this line here is for visualization. PPTabs. Okay, but save big example.png. Load example.png. let's put this in plots directory. Example.png. So here you see that you can save it into a plots folder. Get it. This is begin. And so we got time to do this. Begin and end. Let's do this. No, T bias. Yeah, okay, very good. T bias. Try this again. Okay, so here you see an example. So okay, so this is the file that I preloaded as an example. So with Pluto notebooks, for example, you can have sliders, for example, and then you load the data, and then you can plot the data. It's still yeah, this is the plotting. This part is the plotting here. Oh, I forgot this. List. Forgot to load the NetCDF dataset. So for example, with the Pluto notebook, you can, for example, toggle stuff. For example, you can toggle the domain size. So you can toggle the domain size, and then it will run everything all over again. And then see, for example, this in this case, yeah, you see that the title here has changed. So for example, with Pluto notebooks, this is an example of what you can do. This example that I use for my projects, for example. And then for here, in this case, I created an example of a Pluto notebook from scratch where I loaded some data, and then I showed you that you can plot and visualize. You can load the data and you can plot and visualize it in Pluto as well. So that is an example of how I use Pluto notebooks in order to, and if in this case, for example, if I wanted to change the scale such that it's a log scale, then I can do that as well, for example. So things like this, that I find to be very things like this that is reactive, it's easy, and it's generally quite fast. And unlike Jupyter notebooks oftentimes saves the output and saves the figures. So sometimes your Jupyter notebooks can be quite big, quite large in terms of file size. Pluto notebooks are purely saved in Julia. So whenever you load the notebooks, you don't have anything stored in them. So this image, for example, in Jupyter Notebook, it will be stored in the Jupyter Notebook. But in Pluto notebooks, everything you will have to, again, run everything from scratch. But while I think the upfront time is the upfront time is larger, I find that the reactivity when you do things like toggling the domain size, you can make selections that change your experiment name, for example, and then you can change a figure, you can change whether to save something or not. I think these are pretty useful. I think these are pretty useful tools. These are pretty useful tools to have that you can use to explore your data on a remote server, explore data sets, explore model runs easily, and visualize them like on the spot. Like if it hadn't been for the fact that the server crashed on me, I would have been able to show you guys this like within like 5 minutes or something, So I hope that this has encouraged you guys to think about using Dr. Watson to organize your project and Pluto notebooks to explore your data sets. And with that, I am done. That's the end of my presentation. I hope you guys had fun, or not fun, but I hope you guys learned something from today.
João, you're there. Okay.
Recording in progress.
So this, thank you, Nathanael. This brought us to the end of one more presentation and today's workshop. And I'm sure for us it was very interesting, and I'm sure that it was for those online as well. So I thought, I don't know if we have questions. Did we do questions for Nathanael? Or if there are any questions now, feel free to drop them in the chat. In the meantime, I'll invite Fabio Kleitner and then Nathanael to let us know what they thought about this workshop. If they have a comment about the workshop and the project.
Yeah. Hey. Hi, John. Thank you. Fabio Kleitner here, research at LANCE, and the head of the Earth observation team. I'd like to thank our center and Untitled for the invitation to be here today. As João said, in April, we had the opportunity to organize the first workshop here in Rio. The workshop was an opportunity to present Julia to the scientific community and to the decision makers from various government institutions, as well as private companies in the renewable energy and urban planning sector. Julia has proven to be a very important and a powerful tool, combining data analysis with high performance computing and scientific visualization. Especially in Brazil, Julia can play a transformative role in addressing these challenges by empowering researchers and the professionals to optimize their resources by combining simplicity and with performance. A key point of great significance is to promote collaboration. So Julia's open source nature aligns with Brazil's growing emphasis on open science and knowledge sharing, for instance. So thanks again to all the participants and speakers. Thank you, João. Thank you, Eugenia, Catarina, Adriana. Thank you all. It was a great day of learning and improving our knowledge of Julia and how we can incorporate all the analysis and visualization tools into our work. So see you at JuliaGeo 2025. Thank you.
Indeed. Thank you, Fabio. It will be a pleasure to have you here. It was a pleasure working with you all. Nale, would you like to say a few words?
Yes, thank you, João. I would like to thank Accenture and UN Trade and Development for choosing South Africa as one of the beneficiary countries for this exciting capacity building project that is focusing on developing skills on the use of space technologies and Julia programming language to support sustainable urban development. We also would like to thank also the specialists who came to South Africa in August, and also those who joined online for taking their time to prepare the training materials and also to educate and capacitate the South African researchers on the use of Julia programming language. We definitely learned a lot, and we could also see that there is a huge appetite for using Julia. So this was evident by seeing a number of people, more than 100 people showed interest in attending the workshop in South Africa. So I think the timing of this project couldn't have been perfect, as governments and business people all over the world are taking or are acknowledging the role that space technologies play in building sustainable and climate resilient communities. So we are really grateful for the opportunity, and we're looking forward to also participating or collaborating with everyone who's in the call, especially in the training, especially the sponsors, Center and UNCTAD, and also the specialists. We're looking forward to collaborating with you on developing those insights that takes that leverage from Earth observation data and Julia programming language. We see a lot of value and applications that can be derived from, using Julia. In South Africa, we recently launched a data cube platform, and I think it's one of the projects where we can integrate Julia programming language and some of the tools that are already been presented here to generate those insights and develop those applications that our authorities and decision makers can use. So thank you so much, and also for giving us the opportunity to participate today. It was really an eye-opener seeing those practical case studies presented. Thank you very much, and we're looking forward to working together in the near future.
Thank you, Nelly. It was a pleasure to work with you and to have South Africa participate in the program. And we're going to see you here at JuliaGeo. We're going to see also all the participants from today. Thank you so much, Alexander, Barth, Felix, Cremer, Nathanael. Felix has raised his hand. He heard about data cubes, so I think it's because of that. I was going to set. So now that you mentioned there's a data cube that you're creating there in South Africa, if you'd like to share some information about that, maybe with Felix we can do something in JuliaGeo specific for an exercise involving your data cube. Felix, do you want to add something to that?
Yeah, but I was actually just asking whether you could just provide some more information about this data cube initiative and how Julia would play a role and how we could help, or what might be needed, or
So
whether this is already running, and
if Nala could provide us that information on an email for us to have a look, we could look into this, and it's in the realm of the possible that we could do something specific to that in JuliaGeo 25.
Yeah.
Okay, well, I don't know, Eugenia, are you around? I don't see you here, but I don't know. Well, no. Okay, so somebody told me that Eugenia as well. Well, anyway, anyone, I don't know if Felix, Alexander, or anyone has anything to add. If not, thank you so much for all the participation, or to all the participants, to all the speakers. It was a great event. Thank you for helping us. We see ourselves as part of the Julia community, and we see a lot of value in this, in working with Julia and developing a community. I think there are two things that are inseparable, and we keep doing efforts to promote both. So thank you, everyone. I hope you check JuliaGeo, and if you can participate, whether online or in presence, we'd love to hear from you. Have a good day.
Bye. Bye, everyone.
Bye-bye.
See you in the
Bye-bye.
search.
See you.
Bye.
Bye.
Thank you.